If the bases on both sides of an equation are the same number, then the exponents are equal to each other. So if we have some base b raised to a power of x, and this is equal to the same base b raised to a power of y, since we know the term on the left side equals the term on the right side, and the term on the left side has the same base as the term on the right side, then this must mean that their exponents are the same in order for this to be true, letting us know that x is equal to y. So in a case such as 2 raised to a power of 8, if this is equal to 2 raised to a power of 2y, then we can set the exponents equal to each other in order to solve for the variable. But what do we do if the bases on both sides of the equation are different from each other? If the bases on both sides of an equation are different numbers, then the exponent or exponents can be moved to the coefficient by taking the logarithm of both sides of the equation. So let's say we had 7 is equal to 9 raised to a power of x. We'll use the power rule of logarithms to bring this variable down, making it a bit easier to solve for x. So 7 is equal to 9 raised to a power of x is equivalent to taking the log of both sides. So that would give us the log of 7 is equal to the log of 9 raised to a power of x. And we can use the power rule to move this exponent to the coefficient. We can also take the natural log of both sides, making it the natural log of 7 is equal to the natural log of 9 raised to a power of x. And again, we can move this exponent x to the coefficient using the power rule. So throughout the remainder of this section, I'll be using logarithms, but just know you can also take the natural log of both sides if you wanted to. But let's walk through this example from the beginning. You'll be asked to solve for x and to check the answer. And you're given 7 is equal to 9 raised to a power of x. So step 1, make each base the argument of a logarithm. So we'll make this base 7 the argument of the log of 7. And we make this 9 raised to a power of x the argument of the log of 9 raised to a power of x. And now step 2, move the exponent x of the argument to the coefficient here. This would then give us the log of 7 is equal to x times the log of 9. And now that we've brought the x down, we can solve for x, so that's step 3. And we can do so by dividing both sides by the log of 9, showing us that x is equal to the log of 7 divided by the log of 9. And at this step, you can now plug this into your calculator, and we would find that x is equal to 0.885. And now you can check the answer by plugging this value of x into the original equation for x to see if this equation is true for this value of x. So when we plug in 0.885 in for the exponent, if we plug into your calculator 9 raised to a power of 0.885, you'll find that it's equal to 7, making this equation true. So that is how we go about using logarithms to solve exponential equations. Let's now have you try a few practice questions. Solve for x and check the answer. Question number 1. 5 raised to a power of x is equal to 8. Question number 2. 6 raised to a power of 2x is equal to 14. In question number 3, 2 raised to a power of x plus 3 is equal to 7. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1. We're solving for x for 5 raised to a power of x is equal to 8. Step 1, make each base the argument of a logarithm. So that would give us the log of 5 raised to a power of x is equal to the log of 8. In step 2, move the exponent x of the argument to the coefficient using the power rule. So that would give us x times the log of 5 is equal to the log of 8. And now that we brought the x down, we can solve for x by dividing both sides of the equation by the log of 5, showing us that x is equal to the log of 8 divided by the log of 5. And if you plug this into your calculator, you'll find that x is equal to 1.3. And now we can check the answer by plugging 1.3 into the original equation for x here. So when we do so, we have 5 raised to a power of 1.3, proving that 8 is equal to 8, letting us know that x is equal to 1.3. So that is the answer to question number 1. Let's now have a look at question number 2. We wanted to solve for x, and 6 raised to a power of 2x is equal to 14. Step 1, we want to take the log of both sides. So we'll make each base the argument of a logarithm, giving us the log of 6 to a power of 2x is equal to the log of 14. And now that we have logarithms, we can use the power rule to move this exponent 2x down to the coefficient here, giving us 2x times the log of 6 is equal to the log of 14. And now we can solve for x. So we'll begin by dividing both sides by the log of 6, showing us that 2x is equal to the log of 14 divided by the log of 6. And the log of 14 divided by the log of 6 is equal to 1.47. And now to solve for x, we divide both sides by 2, giving us x is equal to 1.47 divided by 2, meaning x is equal to 0.735. And now we can check the answer by plugging this value of x into the original equation here for x, which would give us 6 raised to a power of 2 times 0.735, giving us 6 raised to a power of 1.47. And we plug this into our calculator. This confirms that 14 is equal to 14, meaning that x is equal to 0.735. So that is the answer to question number 2. Let's now have a look at question number 3. We're solving 2 raised to a power of x plus 3 is equal to 7. Step 1, make each base the argument of a logarithm, which would give us the log of 2 to a power of x plus 3 is equal to the log of 7. And now we want to use the power rule of logarithms to move this exponent, x plus 3, to the coefficient, giving us x plus 3 times the log of 2 is equal to the log of 7. And now we can solve for x. So we'll begin by dividing both sides by the log of 2, showing us that x plus 3 is equal to the log of 7 divided by the log of 2. And the log of 7 divided by the log of 2 is equal to 2.8. And now we can subtract 3 from both sides, showing us that x is equal to 2.8 minus 3, which is negative 0.2. And we can check this answer by plugging it into the original equation for x here in the exponent. When we do so, that gives us 2 raised to a power of negative 0.2 plus 3 is equal to 7. And negative 0.2 plus 3 is equal to 2.8. And 2 raised to a power of 2.8 is equal to 7, confirming that this was the correct answer for x, negative 0.2.